Hello and welcome to our lesson 2 of topic 2. Lesson 2 will feature the mathematical methods of cost estimation. Now, mathematical methods involve visual fit or scatter diagram, linear regression analysis, learning curve effect, and time series, among others. Now, starting with visual fit diagram or scatter diagram, this one is where you have a diagram or a graph with the variables. Let's say you have the cost here and you have the output on the x-axis, the cost on the y-axis and the output on the x-axis. Then this diagram or graph will be used to plot in a scattered way the information or the cost data, assuming that we are having the cost and we have the output. Let's say maybe it's a cost of, say, 1,000, 1,500, 1,200, 2,000, and we have the output. Let's say the output is like 15, 20, maybe we have 12, say we have 30, like that. So this kind of data, when plotted on a Cartesian plane, which is the graph, and assuming we have our coordinates in this version, then we would require to plot a line of best fit that would cut across in the most fair way. And therefore, assuming that this is our line cutting the most fair way, this being the line of best fit, line of best fit. Now, to determine the cost function, which is y equals to a plus bx, using visual fit, then we are supposed to determine the a as the y-intercept. Y-intercept is the value of y x is 0. So meaning at this coordinate where x is 0, then the value of y is where this line extended will actually cut the y-axis. So this is going to be now our a. Then to get our b, which is the slope, the change in y over change in x, we can just estimate, like we can estimate somewhere this way and this way, where this would be our change in x and this would be our change in y, assuming that we take this coordinate here. So this will be our change in y. So we are going to determine the value of b, which is the slope, by change in y over change in x. We get our b. So that we are going to come and substitute, assuming that we get our a. Assuming we get our a as like say 500 600 shillings, and our b we get it as, let's say 20 or either say 50. So we'll have our y equals to 600 plus say 25x. Now our point of concern is this, and that's why we may not be able to do a question and determine using the visual fit, because of accuracy. Since when you are having this data scattered and you're coming up with a line, there is no format or there's no formula of coming up with this line. And therefore, most of you students will have different lines. And when you extend your line towards the y-axis, you'll have different figures. Like this 600, someone will have a 605 or 610, someone will have a 590 or so. So therefore, we are not going to do a question using the visual fit, but I had to demonstrate to you how you would use the visual fit and come up with the function y equals to a plus bx. So this is the way the visual fit would be, but would not be able to use a question officially and come up with the function, because that would be as per my estimation. But that's how you would come up with the cost estimation function. When you come to linear regression analysis, then that time now we are going to use a formula to come up with this line of best fit. It's going to be out of a formula. Therefore, all of us, all the students will have the same line because it's out of a formula. So therefore, we would actually look at it. So this is a linear regression analysis. Now, what is linear regression analysis? So you'll say there that this is also known as least square regression analysis or least square method, which is a statistical technique that analyzes the relationship between the independent variable and the dependent variable. This method is used to develop equation that predicts the unknown value of a dependent variable from known values of independent variables. This means if you're coming up with y equals to a plus bx, then this is what we're calling the dependent variable, while this x is the independent variable. And therefore, we are saying this one is unknown, and that's why we are calling it as unknown. We're calling it as, and this one is known. When we are doing the prediction, it is this value that you want to know. And we can only know it with the assumption that we know already the independent variables. For example, the independent variable can be the output. So assuming that we know what we want to produce, then automatically we are going to determine what costs we shall incur in the production. And therefore, we are calling it as a method of determining these dependents out of the independent that are known. Then a regression equation identifies an estimated relationship between the dependent variable and the independent variables. So we see that we come up with a regression equation that's going to tell us about the dependent out of the independent, either one variable or several variables, depending whether it is a simple or it is a multiple equation. Then the equation can be simple or multiple. Now, when the equation include one variable or one independent variable, then we call it a simple regression. But when the equation has more than one independent variable, then we call it as a multiple regression. So in this case, when we talk of simple, this is like a simple regression, then we mean that we are having y equals to a plus bx. That means one independent variable. And we can say here that where, so y would be the dependent variable, x would be the independent, then a would be the y-intercept. This y-intercept means constant. That is value of y when x equals 0, while b is the slope, or what we call the gradient, or even what we call the coefficient coefficient of x. That is change in y over change in x. We can also get it through changes. If we have the data for x and y, then you can say the change in y over change in x. Now, we are having one independent variable. We are calling it a simple regression. But if you are having like a multiple regression, then this means we are having more than one variable like this. We have y equals to a plus b1 x1 plus b2 x2 up to bn xn, depending on the number of independent variables we have. So you see, we have 1, 2, and several up to xn. That means we are having more than one independent variable. That is what we call multiple regression. But this is where we have one independent variable. That is simple regression. So starting with the first one, which is simple linear regression, where we have said that we use one variable which is independent. So we can say that this method determines mathematically the regression line of best fit. This line of best fit is y equals to a plus bx. This is the one that is going to give us this line that we were estimating when we are doing visual fit. So we'll use the formula there. And then it is based on the principle that the sum of squares of the vertical deviation from the line established is the least possible, that is less than the sum of squares of the vertical deviations from any other line that may be drawn. This is what I mean. That if, for example, we are having this as our line, let's say this is our line, which is now the regression line. We are saying that this regression line is the one that is going to give us the least. If this is our value here, the difference between these two, the line and the variable, which is, this is now our coordinates, that difference we are saying is the least possible. This is least possible deviation. And this deviation, we can have it as, that is, summation of, so let's say y minus y predicted squared. This is what I'm calling the least square method, that this one is minimum. We ensure that the difference between this value, this coordinate is our y, while this line, which is a regression line, we are referring to it as y predicted. That's why the difference between the 2 points, we are saying being the deviation should be as minimum as possible. And that's why we are calling it as least square method. So least square means that square of the difference should be the minimum possible. Now, when talk of simple linear regression, we can have the official equation, the form of the equation. So the form, which is general form, is given as y equals to a plus bx plus e, where we had already indicated that y is the dependent variable, x is the independent variable, a is the y-intercept, which is constant, or the value of y when x is 0, and then b is the slope or the gradient or the coefficient, which is determined by taking the change in y over change in x. This e, it is for any error that may not be explained. So we can say that where this E, or else let me have it as just small letter e. So E represents the error term. Now error term means as we are doing our prediction, our regression line may be erroneous or either may not estimate with accuracy. And therefore, that bit which may not be explained by the regression line is going to be explained by an error. That one we are putting here to ensure that our y is now explained fully by the whole of this together. But without that e, then that means that our y may not be explained by only this bit, unless otherwise under accurate conditions. But in most cases, we have that error. That's the position. Now, these a and b that are constants, we can determine them here. So determination of parameters a and b. How determine these two parameters? They are constants anyway. They are constants. Now we determine them officially using formulas like this. We can have Roman 1. We have this being our regression equation. We can use what we call simultaneous equations, where the first equation we can sum up our regression line. Like now we sum up this is y, we sum up it, it's going to be summation of y equals to, we sum up this a, now a being a constant, and if you're having such kind of data and determine that this a is 600, which is a constant, then it means inside here you have 600, here you have 600, here you have 600, and even here you have 600. That tells you what? Instead of us summing up the 600 that way, we can just take that 600, which is constant, and we multiply by the number of the data items. So that means instead of us summing up that way, we normally sum up this way. We take n, a standing for the 600, and then n standing for the how many number of data we have. Then plus, we sum up this x. So it will be a b, then summation of x. B, summation of x. Then, that's the first equation. The second equation to form the simultaneous equations is where you multiply the regression line by x. So this y times x will give us summation of xy. Then this a times x will give us a summation x, while this bx multiplied by x will give us b summation x squared. That is how we can obtain the two simultaneous equations. And when we substitute the values here, we'll be able to get a and b, which are the constants. Alternatively, we can have these derived formulas. This is derived formulas or formulae. This way, we can have b direct. B is given as n summation xy minus summation x summation y. You divide by n summation x squared minus summation x. You square it on this formula. That will give you b. Then a, we can have it as summation y minus b summation x. You divide all this by n. Or you can have this way, that it is y bar minus b x bar. This means y bar is the average of the y, which means summation y divided by n. You get it as y bar, as a mean. Then minus b. Then this x divided by n is x bar. So if you have the values which are averages, you can still substitute them here and you get your a. Otherwise, this is a formula. So these two approaches, either simultaneous equations or derived formula, this one can be used and we get our a and b parameters, which we are going to substitute in our equation, and that becomes our regression line. So we'll use an illustration to understand and come up with this summation of y value, xy, x, and even x squared using an illustration question. Now, before I give the question, let me just give some assumptions, then we do a question to calculate. There are some assumptions I'll give. The assumptions of linear regression analysis, number one is that there is linearity. That means the dependent variable and the independent variables are related in a linear way. Then number two, the independent variable, which is x, is assumed to be known, while the dependent variable y can be determined from that known value of x. Then number three is that the error term is assumed to be normally distributed. Error term is normally distributed. And number four is that the error terms have a zero mean. So they have a zero mean. And next is that the error terms have constant variance. They have constant variance. Next one is that the observations and the error terms are independent, meaning no serial correlation or what we call autocorrelation. That there is no pattern of the observations, neither do you have pattern of the errors. Then last one is there is no significant relationship amongst the independent variables, meaning there is no multicollinearity. Now this means that if you are having more than one independent variable, they should not be related at all. So you should have a very low degree of correlation. Now later we'll do some tests concerning these assumptions to see whether they hold on a particular question. But meanwhile, we'll do a question to understand how to come up with the regression line before we come to evaluation. So the question is a December 2009 of Advanced Management Accounting, previously known as Management Accounting. Question 1, December 2009, question 1, part A. The question reads that Zawadi Limited, a manufacturing company, is in the process of preparing its budget for the upcoming production periods. The following data relates to the company for the year ended 30th of November 2009. You are given the year column, the month column, the machine hours column in thousands, and the electricity expense column in shillings thousands. The year is 2008, then 2009, down up to the month of November. The month column we have December, January, February, March, April, May, June, July, August, September, October, and November. So if I read across, then the first year, which is 2008, the December month, the number of hours are 51, while the cost is 960. The year 2009, January, 45, 930 as the expense. February, 51 hours, and we have 930. March, 58.5 hours, and then 885 shillings. April, 63 hours, then 750 cost. May, 48 hours, 795 shillings. Then June, 39 hours, 750 cost. July, 39 hours, 750 cost again. Then August, 46.5 hours, 798 shillings. Then September, 52.5 hours, 825 shillings. October, 64.5 hours, 870 shillings. Then November, 72 hours, then 1020 shillings. The total annual and monthly average expenditures for the year ended 30th of November 2009 were as follows. You are given the machine hours. Annual total machine hours are 630,000, while electricity expense is 10 to 60,000, which is 10 million to 60,000. Then monthly average machine hours is 52,500, while electricity expense is 885,000. Then required, estimate the fixed and variable elements of the electricity expense using 1, the high-low method, and then 2, the least squares regression analysis. So high-low method and least square regression analysis. And that is the end of the question. Now, in order for us to use high-low method and also the linear regression, as per the question, requiring us to use the high-low method, we'll have it simply this way. High-low method. We'll have it the way we did previously in the lesson 1, that we took a summary of this being machine hours and this being electricity. So we want to use Roman 1, which is high-low method. So we have high and we have low. These are points, high, and low points. So in our case, if you check from the question, then we have the highest point of the hours is in November, which is hours are 72, while for the low is 39. Low is 39, so 39 hours. While the cost, the highest is 1020, while the low for the cost is 750. So with this now, we are able to work out this y equals to a plus bx. So b we know is the change in cost over change in hours. So change in cost will be the 1020 minus 750. We divide by 72 minus 39, which is going to give us the difference of 1020 minus 750, which is 270. We divide by 72 minus 39, which is 33. So this when you divide, you'll get 8.18. So this will get B as 8.18. Then you substitute this one the way we did using one of the pairs. We can take like the high pair. We say here that therefore 1020 equals to A plus 8.18 in bracket 72 hours. So this is 1020 equals to A plus the 8.18 times 72 will give us 588.96, which in actual sense this A will give us an average of, you subtract from 1020, this would give us 431.04. Now that means we are told to come up with the fixed and the variable. So you can say that therefore we have fixed electricity cost. This is shillings 431.04. That is in full shillings 431,040. In full shillings 431,040. Then the variable cost. So variable electricity cost. This is now the shillings 8.18. This is per hour, per machine hour. So you are asked to use high-low methods to come up with the fixed electricity cost and the variable electricity cost. So we have the 431,040 in total, and we have the 8.18 per machine hour. That's all about high-low. Then you go to linear regression analysis. So linear regression analysis, where we require to use the formulas, which the formulas have indicated there. So I've indicated the formulas, so you just need to substitute them. So the formulas are as per what I gave, either the first one or the second one. So at this level, you would prefer to use the derived formulas, where we can get B directly and you can get A directly. The only difference, or the only activity or task ahead, is to determine the values of x squared, the values of x, values of y, values of x, y, and all that, so that you can be able to use these formulas. So in this case, we'll have to have some columns for us to have these values. So this being the first question, or the first illustration, I'll have the question, all the columns under the values. Otherwise, later we'll be using the calculator to give us the values. So we are going to have this way. So machine hours would represent our x, electricity is going to be our y, then you are going to have x, y, we have, and even you have x squared. So if we space them, we'll have x, we'll have y, we'll have x, y, and we'll have x squared. So if you are to indicate these values, so like if it is a machine hours, we are having 51, 45, 51 again, 58.5, we are having 63, 48, 39, 39, 46.5, 52.5, 64.5, and 72. These are the values of machine hours. Then to get the electricity cost is as what I had given. This we have 960, 960, 930, 930 again. We have 885, 885, 750, 795. We have 750 here, 750. Again, we have 785. 95, we have 825, 825. We have 870. We have 1020, 1020. Then to get the values of x, y, we'll just need to multiply x and y. We'll have this way, 51 times 960, which is 48, 960. My values, I'm storing them as I indicate. I'm storing so that I can have the final answer here. I am having 45 times 930, 930, which is 41, 850. 51 times 930 again. This is 47, 430. 58.5 times 885. This is giving me 51, 772.5. 2.5. Then you have 63 times 750. 750, which is giving me 47, 250. Then 48 times 795, which is giving me 38, 160. Then 39 times 750, 750, This is giving me 29 to 50. Then 39 again times 750. This is giving me 29 to 50. 46.5 times 795. This will give me 36,967.5. 52.5 times 825. This will give me 43,312.5. Then we have 64.5 times 870. This will give me 56,115. And lastly, 72 times 1020. This will give 73,440. So this, when you add, I just need to recall my memory, and it is 543,757.5. That is it. Then, that being my values of xy, to get the values of x squared, I just need to square these values. So I'll be squaring as I store. So I'll be having 51 squared. This is 2601. 45 squared. I'll be having 2025. 51 squared is 2601. 58.5 squared is 3422.25. 63 squared is 3969. Then 48 squared is 2304. 39 squared is 1521, while 39 squared again is the same figure of 1521. 46.5 squared is 2162.25, while 52.5 squared, this will give us 2756.25. 64.5 squared, this shall give me 4160.25, while 72 squared, this will give me 5184. When I recall my memory on the calculator, which it will give me 34,227. So that means if I need again to get these totals here for y and for x, I'll add the columns, and the columns would give me, I am having 51 plus 45 plus 51 plus 58.5 plus 63 plus 48 plus 39 plus 39 plus 46.5 plus 52.5 plus 64.5 plus 72. That would give 630. 630, which was even provided in the question. In the question, you were given the totals, so 630, while this one would give us 10 to 60. As per the question, you were given those values in thousands. So that, or those are the values we want in our formulas, which we have already our summation x, summation y, summation xy, summation x. So this is now our summations. So if you are to substitute now this in our equations here, then you will have this. So we use the derived formula approach. So this being our formulas, we need to now to substitute. So we need b equals to sub n summation xy minus summation x summation y, divide by n summation x squared minus summation x u square. So we can have it this way now. b equals to n is counting how many they are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 months. So 12 in bracket xy. xy is this, which is 54, 37, 57.5 minus x and y. Summation x separately, 630 times y separately is 10 to 60. All this, if you divide by n summation x, so n is 12. Summation x squared from the table is 34,227 minus x, summation x alone, which is 630, you square it here. Square it. So in our case, on the numerator, so this you can calculate once. On the numerator, you can have 12 times 54, 37, 57.5. Then you subtract 630 times 10 to 60. This is going to give me 61 to 90. When you divide by, we have 12 times 34,227 minus 630 squared. This will give me 13,824, and therefore the final answer, which I take 61,290, I divide by my answer here, I'll get 4.43. That is our B, or the variable cost. Then I substitute this one here. I can have it as A equals to, we have the formula as summation y minus a B summation x, all this divided by n. So that means summation y, which is 10 to 60 minus B, which is 4.43. We multiply by summation x, which is 630. So this one, we can divide all this by n, which is 12. So this one will give us 10 to 60 minus 4.43 times 630. This will give us the 7469.1 divided by 12. So this will give me, divided by 12, this will give 622.425. Since we have our B and A, we can now substitute them in our equation, which is y equals to a plus bx, this one, so that you can have. And even before we substitute, since we were asked to determine the fixed electricity and the variable electricity, you can have it this way, that therefore fixed electricity cost is actually shillings 622.425, or in total shillings 622,425 in total. It's like that. Then the variable. So this is variable cost is going to be shillings. It was how much? It was 4.43 per machine hour. So if you were to come up with an equation, even though not asked, an equation, then that equation, the cost function that is, would be therefore y, which now we can say is our regression line. Our regression line would be y predicted, because we'll be using it to predict the future cost, will be equals to 622.425 plus the 4.43x. This means that should we want to predict for the next month, let's say like December 2009, then we have the number of hours, we'll just come and substitute here, and we get our total cost. Now, most importantly, to distinguish between the high-low and the linear regression and see the accuracy of it, and which is most appropriate. First of all, we had the assumption or even the limitation of high-low that it uses only 2 points and ignores the rest of the data, meaning we cannot rely on the estimate of fixed and variable. And that's why you see the fixed is 431. Fixed was 431 point, while this one is 622. That means high-low, the fixed cost is underestimated, while the accurate one would have been 622. Then the variable cost, this is actually 8.18 variable cost, 8.18 per every hour, while this one is 4 point. This being the accurate one, automatically that means that the high-low variable cost is overstated. That means variable cost is overstated, fixed cost is understated. That will have an effect if we were to substitute next year's or next month's number of hours. So this regression is taken to be more accurate as compared to the high-low methods. So we have come to the end of lesson 2, that we have featured the mathematical methods, 2 of them, the visual fit diagram, which we did not do a question actually, but I explained how that line of best fit would be established, but there would not be any formula to get that line. But in this regression, the line is going to be estimated this way, that you have estimated where the y-intercept will be, and also where the gradient now would be 4 points. So if you are to draw that line, we would have the same line all of us, because we already have the values and we just substitute. That is the beauty of regression. Even though it is going to be tedious coming up with these, though we can also use there's a way we can use a calculator and have these values very fast, which I'll show you in lesson 3. This is taken to be very accurate and is reliable. We can even measure the error, the probable error. This we are going to do in the coming lesson 3. I'll show you all that together. So that is it about the regression as far as estimation is concerned. That's the end of lesson 2. We meet in lesson 3 in the same topic, which is cost estimation. Thank you, everyone.